Bruh. Good morning, fellow mathematicians. Welcome back to another video. You might have not thought that this could happen once again in your life, but Papa Flammy is still doing differential equation theory stuff, and today we are going to take a look at exact differential equations. And we are going to dive right in. At first I would like to give some motivation and kind of a little definition for exact differential equations, exact differential equations the German boy came through. At first we are going to take a look at the total derivative of some certain function f, where we have to place restrictions on it later in the game. Give me a second for that, okay? At first, you might have never heard of the total differential before. If you did, well, hooray, you're already knowing what's coming next. So the total differential of this thing right here is basically nothing but the partial differential of f in the first variable, x in this case, times a differential dx plus our function f partially differentiated with respect to the second variable times dy being equal to 0. Okay? And you can make this arbitrarily large depending on the number of variables you have here. This is just a function in the xy plane basically. And if we are dealing with the xy plane, I want you guys to notice that if we have a curve right here, for example this integral curve, nice piecewise continuous function, this thing right here is actually labeled with an x and y, x, okay? And y right here is as always independent of x, meaning this f of xy is actually f of x comma y with respect to x, okay? Just as a little side note, we need this in a second. Now, we can play physicist here, and in one dimension it actually does work out wonders, because limits in one dimension are nice to handle, okay? Why not divide both sides by the x? It's not equal to 0, it's just really close to being 0, okay? Let's divide both sides by x, that's nice and rigorous right here, dx, not x. Then we are going to have this chunk right here, plus del y of f, dy, dx, being something like 0 over something, which is just 0, okay? This is just how it is. Okay, now we have this right here, and let me give motivation for the next thing. The chain rule in more than one dimension. Let's take a look at a multivariable function, f with respect to x, comma y with respect to x, being nothing but, for example, x times y squared, for example. What happens if we differentiate this function f only with respect to x, okay? ddx of f. Well, basically we are going to end up with the product rule at first, so differentiating this thing with respect to x simply, and then we are going to differentiate this part once again with respect to x, but this time on the variable y right here. I hope you know how the product rule works. Meaning we have 2 times x times y, but also y is with respect to x, meaning we have to use the chain rule right here. So times dy dx. And I hope this does make sense to you, because this thing right here was basically nothing but the partial derivative of f in x, and this little part right here is nothing but the partial derivative of f in y. Meaning this thing right here is exactly of the form that we have right here. Meaning what we have here, this homogeneous differential equation, is basically nothing but the derivative of f in x being equal to 0. And you see here what happens, for example, if we differentiate the number pi, which is 3, which is 2, which is e, which is square root of g, which is nothing but 4. Well, if we differentiate a constant, it's going to be 0. And meaning f is actually just constant. Our general solution to an exact differential equation is thus given by a one parameter family of solutions. Okay? That's just something I wanted to talk about. So what's the cool thing about f right here? Well, our f, we want it to be continuously differentiable. Yeah, we want it to be differentiable and also continuous. So that's something cool. Because let us rewrite del x of f right here. We are going to call this thing p, and we are going to call this thing q right here. And once you differentiate f, if it's continuously differentiable, p and q are also going to be continuous, meaning they are also differentiable. We need this in a second for our theorem. Also, one little thing, we want f to be defined on a simply connected curve. So a simply connected region in some way, for example, like this right here. This is simply connected. What's not simply connected is if you would have like a circle in here, or if you would have an 8, for example, if it's cutting itself. Also, our theorem that we are going to talk about in a second is only going to hold for a rectangular domain in this case, where all the lines, where the whole rectangle lies in our simply connected region. So what wouldn't work is if we would have this thing right here, okay? This rectangle wouldn't work. Our theorem only holds for a simply connected region where our f, q and p are actually defined, and the whole rectangle needs to lie in our region. Just a little thing I want to talk about, and that's a little intuitive explanation what I was talking about a second ago. So now let's take a look at our theorem, our boy of the day. So, we are calling this differential equation right here exact. If and only if, I just hit my ring on the blackboard, that hurts. If and only if our partial derivative of p with respect to y is the same as our partial derivative of q with respect to x. And we actually call this thing right here an exact differential equation. That's the definition right now. This differential equation is exactly exact if our p can be written as del x of f and our q can be written as our del y of f. Okay, meaning what we have to basically prove right here is that those two exist if and only if del yp is equal to del xq. Meaning we have to prove a little forward direction and a backwards direction. Let us start with the first one. From left to right, it basically states that let del x of f be equal to p and del y of f be equal to q. Just take a look at Wikipedia if this right here doesn't ring a bell for you. So there are many theorems out there which basically state the same thing. This is just what I'm working with, okay? So now we are going in this direction, meaning what we want to show is that del yp is the same as del xq. How can we show this? Well, we want to get to del yp and del xq. Meaning, why not just differentiate p with respect to y and q with respect to x, okay? And also p and q are functions with respect to x and y. Once again, multivariable functions. Meaning, del yp is the same as del y of del x of f. And we also have that del xq is nothing but del x of del y of f. Okay, and actually I went through this proof on my own, so I didn't use any sources on this one right here. It's not like with my old ones where I used the analysis notes, for example. That's the proof I went through on my own, and it worked out quite Gucci, if I can say so myself. So this does work out, the second derivative, just because our f is continuously differentiable. Also, if we can differentiate it with respect to x, and we can also differentiate it with respect to y, there does automatically exist a second derivative, a second partial one. Okay, now here comes one thing into play, which is a theorem in analysis. Maybe you have heard of it before. It's Papa Schwarz theorem. What it only states, if certain conditions hold, and the conditions that we need hold, so f is continuously differentiable. Also, we have defined it in a simply connected region R. We can actually interchange our order of differentiation. Mixed partial derivatives under certain condition are actually interchangeable. You can go through all the conditions. It's just a matter of interchanging limits actually. Okay? It's just a partial derivative. And meaning overall, that by Schwarz theorem, del squared, del y, del x of f is the same as del squared, so that's just a mixed partial derivative, del x, del y of f. But what does that mean even further? Well, we know that equals to is an equivalence relation in the real complex whatsoever numbers. It's transitive, meaning if 3 is equal to 5 minus 2 and 3 is equal to 4 minus 1, then that also means that 5 minus 2 is the same as 4 minus 1. What I want to get at is that del yp is the same as del xq, just by this relationship right here, okay? That's also equivalent to saying that del yp is the same as del xq. Okay, this has been the first implication, and now for the second one, which is going to be the real thing right here, the hard part, I would say. See you in a second. So this next part is basically just a matter of construction. So many proofs involving differential equations are actually just proofs where you construct yourself something and you hope that it works. So if you have to watch through my differential equation playlist, you might already know what I'm talking about. So let us once again talk about what we actually want to show. We are going to say that those two partial derivatives are actually equal. And what we want to prove now is that this thing right here is exact, this differential equation. Meaning what we want to show is that there exists some function f where the partial derivative of f with respect to x is nothing but our p, and the partial derivative with respect to q with respect to y of our f is nothing but q. I'm terribly sorry. So this is where we want to get at. Now we are going to suppose that such a function actually exists, okay? Okay, we are going to say that some function like this exists, and it's equal to our p, and del y of f is nothing but our q. And with this we are going to work now. Also, like I said in the beginning, or did I say so? We also want initial values to hold. So that's an initial value problem. If you take a look at the plane right there, our initial values, this x0 y0 coordinate, for example, needs to lie in our simply connected region. So now what we are going to do is what we always do with differential equations. We are going to try and solve them. Okay, so at first we are going to integrate our p. Okay, we are going to integrate p with respect to x. So from x0 to x, p of x comma y with respect to x. Okay, if you don't like that an x is right here and up there in the upper bound, just use a t in here, okay? Really doesn't quite matter what you use at this point. What exactly is that? Well, this is nothing but this. We are supposing that it is. So that's from x0 to x, our del x of f integrated with respect to x. And now, if we have a function and we differentiate it with respect to x and then integrate it with respect to x, what is this going to give us? Well, it's just a function itself with the upper and lower bounds plugged in. So for example, if we differentiate x to the third power, it's 3 times x squared. And if we integrate this once again, it's x to the third power just with the upper and lower bounds plugged in. So basically that's the function in x and y. We are integrating it with respect to x. We are going to let the y stay constant. So this is nothing but f of x comma y, the upper bound plugged in, minus f of x0 comma y, the lower bound plugged in. And like I said, we want our initial values to hold. And this thing right here is part of our simply connected region. It's just a certain coordinate, y and x0, okay? Now, I want you guys to notice, if we have this function from before, f of x comma y equals to x times y squared, okay? What happens if we plug in our initial value, x0? Well, then that thing is going to be f x0 times y squared. Well, x0 is a certain value. It's not something you can plug any numbers in anymore. Meaning this function in itself is just with respect to y now. So we made our x value constant right there. It's an initial value. Meaning this thing right here is actually just some function with respect to y. So let's call it r with respect to y. Okay? This is what we have right now. Now, why not add this on both sides? Okay? Now we are going to get that f of x comma y is basically nothing but r of y plus the integral from x0 to x of p integrated with respect to x. Now, we have this function with respect to y, and it's basically just the constant of integration. It's a function of integration, and when solving differential equations we always want to know what this actually is. We went through this process already when solving second order differential equations or non-homogeneous differential equations, I'm terribly sorry. We were actually differentiating both sides there and then integrating it once again with some initial values, and we were taking a look what we actually got. Now, why not differentiate both sides with respect to y? We are going to get del y of f is nothing but, okay, the derivative of r with respect to y is just r prime, let's put it like this, of y, plus the partial derivative with respect to y of this thing. We can make use of the Leibniz rule. X and x0 are not dependent on y, meaning we can just bring it to the inside as the partial derivative. It's just a special case of the Leibniz rule, meaning that's nothing but the integral from x0 to x of del y p xy integrated with respect to x. And here comes our assumption in. So you can't do proofs without the assumptions from one direction to another. We exactly said that del yp is nothing but del xq. So this thing right here is actually del xq. Now, how does this help? Well, it's the same procedure as before. If we differentiate a function and then integrate it in the same variables, just this function in itself with the upper and lower bounds plugged in. So this thing is going to evaluate to r prime of y plus q of x comma y, okay, plus q of negative, that's the second part of integration, I'm terribly sorry, q of x0 comma y. Now, what is del y of f? By our assumption, we were supposing that such a function actually exists. Del y of f is nothing but q of x comma y. Meaning this thing is the same as that. We can cancel it out on both sides. Meaning overall that r prime of y is actually nothing but q of x0 comma y. Now we have actually found out what the derivative of our r with respect to y actually is. So we can get back to our r of y if we just integrate both sides with initial values plugged in. Okay. Now, it's a really constructible proof, so it's just something you go through. That's at least the thing I came up with. So if we integrate this from y0 to y, don't forget, r prime is nothing but the derivative of r with respect to y. Meaning, if we take the derivative and then integrate it in the same variable, up and lower bounds just plugged into here. So this is r of y minus r of y0. And I want you guys to notice that this thing right here is actually just constant right now. This thing is just a constant. It really doesn't quite matter anymore, okay? It's just a real constant of integration now, not a function anymore. Being equal to this thing integrated with respect to y. From y0 to y, q of x0 y integrated with respect to y. Now, we can, let me see for a second, it's kind of a lot of stuff we have to go through here. We can actually bring this to the other side if we want, but we also know what r of y actually is. We don't want to miss what r of y actually is. We have found it out before. R of y is nothing but f minus this right here, okay? So we can plug this in. R of y is f of x comma y minus integral from x0 to x of p x comma y dx minus r of y0 being equal to this chunk right here. Actually, let me bring everything to this side, so just adding this on both sides, okay? So we are going to get positive signs right here. Overall, we are going to stay positive in this video. From y0 to y, q of x0 comma y dy. Now, all that's really left to do is to differentiate our f with respect to x and our f with respect to y, and then we are basically done. But since I'm running out of space, I have to erase everything. I'm terribly sorry for this little interruption. So we are close to being done. That's going to be quite a long video. So now, like I said, we are going to differentiate this thing with respect to x. So del x of f is going to give us the derivative of this thing with respect to x plus, okay, this function right here, our x became constant. So if we integrate this, this is just some function with respect to y. With respect to differentiating, with respect to, so much respect right here, press F to pay respect. If we differentiate this thing with respect to x, it's going to vanish. This thing is just a constant, it's going to vanish. So we are going to end up with this thing right here. Now there's something called the fundamental theorem of calculus. Maybe you have heard of it before. But if we now apply this differential to this thing right here, we are just going to end up with p of x and y. This is just how the fundamental theorem of calculus actually works. So I don't think I have to state it right here. If you don't even know that, then you shouldn't watch this channel right here. This is going to evaluate to p of x comma y. Now, what's going to happen if we differentiate this with respect to y? Del y of f. Well, we are going to get del y of this integral p x comma y dx. And then we're going to differentiate this with respect to y. By the fundamental theorem of calculus, we actually know that this is just going to evaluate to this function with the upper value, okay, because this right here stays constant and it's going to vanish in the game. So plus q of x naught comma y, and then this differentiate with respect to y is going to vanish. It's just a constant, just like before. Now what is this thing right here? Well, I'm certain we have talked about this before. That was right here in the first line, somewhere. No, it's not anymore, but this really doesn't quite matter because we can use the Leibniz rule once again, special case, bring this to the inside, and then del y of p is going to evaluate to exactly, by our assumption, del x of q. Oh, I had it on this blackboard right here. So this thing right here is basically just the integral from x naught to x of q of x comma y. Okay, del x. I'm terribly sorry. Okay, by our assumption. Now, differentiating a function, integrating it with the same variable is going to evaluate to this thing with the upper and lower bounds plugged in, leaving us with q of x comma y minus q of x naught comma y plus q of x naught comma y. Meaning this and that is going to vanish, and the differential of f with respect to y is this, and the differential of x with respect to f is this. So, just meaning, if we assume that such a function exists, I'm terribly sorry, then we definitely made sure that this differential equation is exact, because on this rectangle where we have defined it, it satisfies all the conditions that we need. It satisfies our initial values to hold, and you can start from a different way. So originally we have started with choosing this path and integrating this with respect to x, but you can also start from here, integrating this with respect to y, and you are going to end up with nearly the same thing right here, just with this being a function of x naught probably, and instead of an x naught right here you have an x, and instead of a y you are going to have a y naught right here, okay? It's going to result in the same thing. But this proves the theorem, basically. Take a piece of paper, try it out for yourself. It shouldn't be too hard, actually. If you did enjoy this video, please like, subscribe, and recommend channel if you like. And you don't need to remember any of this right here. It's just a theorem that I wanted to prove, just like I do every time with my differential equation playlist right here. We are going to talk about an algorithm to solve exact differential equations like this right here. We are going to talk about integrating factors and inexact differential equations and blah blah blah. But till we come to this point, I thank you guys for watching. If you enjoyed this video, please like, subscribe, and recommend channel if you like. If you want to support the channel a bit more, buy those t-shirts I created. Or support the channel on Patreon. Up until the next video, have a flammable day. It's so warm in here. Love you guys, appreciate ya. Ciao.